Hi, my name is Aryeh. I am a student at UMBC. This presentation is for ENME 475 Robotics, the instructor being Dr. Wu. This is the name of the paper. If you want, you can follow the link, which is called Visual Servoing Spanner Picking and Placement with a SCARA Manipulator. So a little bit about the SCARA. Some applications are it's rigid and durable. It moves faster than regular 6-axis robots. Since the inverse kinematics are simpler, it needs less computational time. Also very applicable to this paper. As you can see also in the following image, vision systems can easily be added to a SCARA. Therefore, let's say if it's doing some drilling and where the tolerance, the hole tolerance are in different spots, can be adapted to accurately screw in the correct spots using the imaging system instead of some other place. Also, the workspace can be held from below by the SCARA, which could reduce foreign particles falling on it. You'll see a picture of that in the next slide. It also has low inertia, allowing the SCARA to be rotate with a high acceleration, allowing it to transfer heavy things from one workspace to another, from one in its workspace from one task space to another task space. You'll see something from that on the next slide as well. So here is it being held below. Here's an example of its high inertia rotating to transport heavy items from one area to another. So this is the SCARA in the paper. It's also good to know that SCARA stands for Selective Compliance Articulated Robot Arm, meaning it's compliant in select direction. Here, in this case, it's the XY plane, and would be rigid in the Z-axis, even though really it can move in the Z-axis, as you see this little piston. There's a close-up to the next slide. However, for the analysis, the purpose of analysis, in the paper, it is simplified to 2 degrees of freedom, even though it actually is 4 because there's also a rotating joint at the end effector. In the appendix, I'm not going to present the appendix here, but in the appendix, I actually go through some of the kinematics of 4 degrees of freedom. So here's a close-up. You can see the piston. Each joint is like 250 degrees here. You can see the 2 joints. So this is a design picture. It's also good to note that the space between the 2 joints is minimal. It's more applicable if we're doing analysis of 4 degrees of freedom. 2 degrees of freedom doesn't even matter because it's in the Z direction. You see it could move this way with the piston, this rotates, this arm here. So now we get into the forward kinematics. So here are the coordinate frames, here are the joint coordinate system. Here is the origin. Notice it's located over here and not here. And also it's good to note that, so here's the DH convention table. It's good to note that this red 0, so Z1, the coordinate frame Z1 is pointing in the opposite direction of Z2. So technically it should be 180 degrees. However, since we're only doing analysis in the XY plane and not in the Z direction, it doesn't affect the position at the end position in the XY plane. If we are doing the Z, then this would become more important. In the appendix, I actually deal with that, the calculations, if this would be pi as opposed to 0. So this is the end transformation using DH notation of our problem. So again, it's only affected by the length of the link, which is 250 millimeters, and since it's the first joint from the origin to the first joint, it's only affected by theta. This part is the rotation. This part is the position. And then from the first joint to the second joint, you have the same thing. Again, since we consider the alpha to be 0, the alpha angle, the angle between the z-axis along the x, then the rotation matrix is not affected, and it's the same thing as this. In the appendix, again, I explore what happens if it's different. And then here are the position vector. So if you multiply, in order to get from the origin to the end effector, you multiply the two to each other in this order, which gives you the following homogeneous transformation. So C12 is short for this whole thing. By the way, the paper did not have the full equation. And then C1, S1, S12, you can all find them over here. So this is the part we're interested in, the position matrix. Z, we're not really dealing with, it's 0, therefore. And anyway, if we only consider the first two joints, it's 0. So this is the X position, and this is the position in the Y direction. So the SCARA's workspace for inverse kinematics is limited by each joint is only 250 millimeters. So if the joint's fully extended, it can only reach 500 millimeters. Also, it's limited to 300. Each joint is limited to 300 degrees, which means it can only swing 150 in each direction. So it could swing like this, and then it could swing like this, but I can't necessarily reach so easily into this space. Maybe it could sort of rotate backwards and shave a little bit off. So this gray area is this is its workspace. It could reach into that, but I can't reach so well in the hexagonal area or the inscribed circle. So this is the this is the paper's calculation for the inverse kinematics to calculate θ1 here and θ2. So θ2 is this, and dependent only on the length of the joint, which is both joints are equal to each other, the x and y coordinate of the end effector, and then θ1 is θ2 minus this theta over, if this is a combination of theta here and θ2. So before I start talking about what I did to test the equations, just want to mention that the task space is the yellow dotted line, is bounded by the yellow dotted line, and the workspace is bounded by this black dotted line. So I chose a point in both the task space and the workspace. So I chose 275 millimeters in the x direction from the origin, and 100 millimeters in the y direction of the origin. And it's also good to note that I tried to line up the coordinates with both the inverse kinematics and the DH notation. So both y's are pointing in this direction. So I first attempted to do a CAD simulation to test out both the DH notation equations and the inverse kinematics. Fortunately, I was not able to have an angle calculator. You can see here is the random point that I chose. This is 275 millimeters from the origin here, and 100 millimeters in the y direction from the origin. Notice that one thing we could see, however, is the angle should be positive here for θ1, and θ2 it should double backwards and be negative. And this is sort of just how the SCARA would move. This would be a simplified SCARA. So for the code, my goal was to first calculate my angles using the length, which is constant, and my random position of xy, and plug that into the DH. So to get these equations, I simply just coded out the equations, the sines and the cosines to get theta 1, theta 2. You see you have your theta, you have your theta 2, and then your theta 1 you get using both theta 2 and theta. Then I would plug that into the DH, those results. So you could sort of see, here's my DH table. This is theta, this is transformation 0 to 1. This is transformation 1 to 2. So, yeah, it's dependent on theta 1 and the theta. This would be, as you see in this function, this is the theta part. Alpha, again, is 0, since we're not factoring the z. And then, so this part actually does the grunt work. These are all the matrices that the A, alpha, the distance, and theta get plugged into. Oops. And then they're multiplied with each other to get the transformation, which is returned. And then I take the two transformations, transformation origin to the first joint to the second joint, which is the end effector, multiply them to each other, which gives me the transformation from the origin to the second joint. So doing the first part, getting the xy of 275 and 100 millimeters, I got theta 1 being 108 degrees, which sort of makes sense. It is a positive rotation, so it's in the ballpark. And then theta 2 is a negative rotation, so it's also in the ballpark. So I plugged those into the DH parameter code. That got me a transformation from the origin to the end effector of 283.73 here. So that's off. This position part of the matrix. You can see that's off compared to 275 and 100. I made a error calculation, and so X, it's not so far off. It's within 5%, but Y, it's more than even 10%. So that's not good. And by the way, here is the code that I used to do my calculation. I did put things absolute just in case there were some negatives in there. So the magnitude of this error is 28 millimeters. And also to give you an estimate of the percent error in terms of from the origin, it's more than 5%. So I also tried several other coordinates in the plus x plus y, they're always off. They tried then several coordinates in the plus x minus y coordinate, they were even more off. And also to point out how big the error is, I estimated that the spanner width is around 25 millimeters. So that means, you can see in this picture, with the error of absolute position error of 28 millimeters, so if the SCARA could think it's really reaching on this point when it's actually on the other side of the spanner entirely. So it may miss it. I was not able to replicate the kinematic accuracy of the paper that the paper was describing. I suspect that the discrepancies in the paper's inverse kinematic section. In the appendix, I actually go through a derivation test, where I used the zero position, some of the zero positions to check my DH table, and it was accurate. However, the focus of the paper was on imaging, so it's understandable such a discrepancy. I'm skipping the appendix area I'm just going to quickly skim through it. You can see that I sort of go through everything more in depth. I go through the law of cosines and sines. And then, so in conclusion, I tried to verify the accuracy of my DH notation and inverse kinematics, my forward kinematics and inverse kinematics, and there was significant error which would possibly hinder the proper positioning of the end effector. I derived the equations more in depth and double checked the work of the paper, and I was not able to replicate the paper's accuracy. It's important that the SCARA should be programmed accurately, especially if it's manufacturing products involving human safety, let's say bolts that are needed in a plane. If the bolts are screwed in the wrong spot, that could create significant failure. And then here are my references. You can click on these links. I hope you enjoyed this PowerPoint.